Yes. Matter, why does it matter? Matter is made up of anything that takes up space or has mass, right? So air around us, a lot of people are under the mistaken impression that the air is just empty space. It's not. There's actually molecules in it. Solid, liquid, gas are the general categories that we use. There's also plasma, which is superexcited gas, and then there's a category below solid that's kind of halfway in between. But these are the three that we're going to talk about in this class. In the particles of a substance, I want you to start thinking about the particles in terms of their proximity to each other. Because matter interacts whether it's really close together or whether it's really far apart. Now, of course, if it's really close together, the matter is going to react more readily. If it's really far apart, it's going to take a long time. For example, gases. In a gas, the particles are very far apart. If you're going to draw a picture of a box with a gas in it, the box would be square, and you'd have the gas particles at random places located throughout the box, right? So they have random motion and complete freedom of motion. They assume the shape of the container. If I had a container of helium up here at the front of the room and I opened up the stopcock on the helium, it would come out and it would expand to the whole entire room, and it would create a homogeneous mixture with all the other gas particles in the room. Gases can be compressed. This is a good example of back when I was in high school in the 70s. I grew up on the west side. I went to Trevor Brown High School, and a lot of fellas had lowrider cars that had a lot of hydraulics. And at lunchtime, we would all go out to the parking lot, and the guys with their cool cars would drive by, and they'd bounce the front and bounce the back, and we'd all clap. It was so fun. And gases have the most energy because they have three what we call modes of motion. I'm going to come back to that in just a minute. Liquids. The liquids are closer together than gases, but they also have freedom of movement, and they don't have complete independent freedom random movement like gases do, but they're able to move past one another relatively easily. Liquids also assume the shape of their container. You can pour it from a tall skinny thing to a short fat thing, and the volume doesn't change. Most liquids aren't compressed very much. Now, there are some that can be, and believe it or not, temperature does affect the volume of a liquid, especially water. And liquids have less energy than gases because they only have two modes of motion rather than gases, which have three, which we're going to come back to in just a minute. Solids are what you see depicted in what's called a crystal lattice structure. You may have seen things like sodium chloride crystals, and they show a little ball and a stick that connects the little balls together. Well, the stick is not really a stick in real life if you have a solid crystal structure. Those sticks are supposed to represent electrons that help bond the individual atoms of a substance together. Now, some are bonded, some are just in a crystal structure by virtue of their temperature, but they have very restricted motion. Solids do. They have a fixed shape. They don't take the shape of their container. They're not readily compressed, and their volume doesn't change, and they have the least energy of all. All right, so there's the three physical states of matter that, why is this not showing? Well, there's a link there that shows you the different states of matter. I'm not able to get it up on my screen, and that's okay. And this is helpful. You can see that this corresponds a lot to what we have over here on the wall. So you look at the colors on the periodic table here. You look at the colors on the periodic table on the wall. Here, what does it mean if it's purple? Solid. It's a solid. Okay, on the wall, how does that correspond? Black. Something that's black, right? That makes sense. Okay. On the slide, what are the things that are liquids? Blue. So we've all seen mercury, right? Mercury thermometers. Mercury is a liquid at room temperature. And bromine is also a liquid at room temperature. Bromine is actually something that's come into use more commonly. A lot of people chlorinate their pools, but you can brominate your pool because it's in what we call the same family. That's the vertical column. And so chlorine and bromine act a lot like each other, and bromine is sometimes actually cheaper, and it's not so burny on the eyes when you use it to clean your pool. If it's yellow, or what does that color correspond to on our periodic table here on the wall? Blue, which makes sense that it's a liquid, right, at room temperature. Finally, what does that mean if it's yellow on the slide? Gas. It's a gas at room temperature. Now, room temperature is what we call standard temperature. And they say, okay, if you're in a building in an average environment, it's going to be about 25 degrees Celsius. So that's what we use whenever we say, okay, if I had a room up to 100 degrees, there'd probably be a lot more of these elements that were liquids or gases, right, than 25. So temperature certainly has an effect on the state of matter of a substance, and that's why we use this. All right, when a solid changes to liquid, we call that, yes?
What about the white ones on the board?
Those are, they don't have, they're not filled in because they're super unstable. Most of those are man-made elements that they fabricated in the lab, and some of them they've come up with names for. The ones that start with a U, I don't think they've actually decided on names for. And once again, it's all because they're so unstable. That's why they're in that sort of white outline thing, that they're not naturally occurring, I guess you could say, right? All right, so we've got phase changes. Now here's where this idea of states of matter and energy comes in. We've got solid, liquid, or gas, and there's a phase change that goes from solid to liquid that we call melting, right? It's also called melting versus freezing, or solidification, if you want to say it in a more scientific kind of way, right? Liquid to gases is vaporization. Condensation is the reverse of that. And whatever energy it takes you to melt a gram of ice, it also gives back that energy when you freeze it. Whatever energy it takes to vaporize a gram of water, you get that exact same amount of energy back when the vapor condenses. And that is a physical change. So that's one of the vocabulary words that you're going to be using today in lab, and that is part of chapter 3, or this chapter on matter and energy, is this idea of a physical change. Now, when water goes from liquid to gas, there's a common misconception that it breaks up into the individual components, that the H2O of water breaks up. Well, that's just not true. And a lot of people have this misconception. I wasn't quite sure where it came from originally, but misconceptions come from a lot of different places. I've seen biology teachers in high school teach students bits of chemistry that they were not sure about, and they come up with explanations that are what I would call misconceptions. So students may learn it in school. There are also popular media examples of particular misconceptions. One of the ones I like, why does it not go in here? Let's see what Gary says, Control P. Well, there was a Land's End ad. Why is it coming up here? Is anybody good with computers in here? I don't know why this is not coming up on the screen. Well, there's a Land's End ad, I'll describe it to you, and it was advertising long johns. In Arizona, we don't have a lot of opportunity to wear long johns, except maybe if you live in Flagstaff, right? So we don't have opportunity to wear long johns in here. But it's an advertisement that says that the long johns are very effective because they wick, W-I-C-K, wick the water away from your skin. And it showed, and can't show you the ad, but it showed in the ad that here's the person's skin, and here's the fabric, and it showed the water molecules starting out like this, and H2O actually looks a little bit like Mickey Mouse, and as it was going through, it said that it separated into the two H's and the O. And I thought, if I was wearing that underwear camping, and I was around an open flame, I certainly wouldn't want to wear that underwear. Why not? There would be a series of small explosions. That's H2. Hydrogen gas, remember the Hindenburg? I'm not wearing underwear that makes hydrogen gas. No, thank you very much. And if it took the oxygen away, that's what we call a free radical. It would be O with a 2- charge, which doesn't last very long. It hooks up to another O and makes O2, and we'd have H2 and O2 next to an open flame. Remember what happened to the space shuttle? That's exactly what happened there. So I would not be wearing that underwear if I was sitting next to a campfire in the Land's End ad. So yeah, let's see. All right, let's see if I can get I can get out of this thing. No, that didn't work.
It's like,
That's not. Oh well, we'll just keep going. We'll just keep going. All right, sublimation. So we've got some changes. We're going from solid to liquid to gas. Where's the ladybug?
watch.
Yeah, you know me. like escape to take
Keep
out of
stress.
the slideshow.
Say that again?
You hit escape to take out of the slideshow.
Escape. Escape is one of these. Oh, here it is. No, it's not doing that.
What are you trying to do?
Control Z.
I'm trying to go Control Z.
Control Z is on too. What is
No.
it? I'm kind of okay with
Control T, switch me around.
It seems like she's mirror monitoring two dual monitors.
Is it going as two separates?
Yeah, it seems like it from the desktop to the laptop.
All right, well, we'll just keep going. Well, now it stopped altogether. My golly.
Call Gary.
So it is two separate.
No, poor Gary has, oh, hot dog, look at that.
Dude, you can just do it in the second class.
I figured it out. We're gonna go to Ladybug now.
Stand shot will be a shoe ball.
Did you see how there's only one? I guess I'll never mind.
Yeah, it's just the two taskbars just hiding from you.
I love seeing the time on the wall.
Now you guys are not seeing that. I think I need to practice this more.
What we got over here. I'm alright with the computer, what are we trying to do? So I feel the type of you're trying to
Well, I want to use the Ladybug and the camera.
So do you want them on separate screens or you want them?
I want to go back and forth. Yeah, behind each other.
So you want to do near screens, you want them to display the same thing?
Yeah.
Last time they gave me a t-shirt. Chris almost got after a certain point, it stopped.
Go back and forth.
So now it should
Close
be on.
this.
It should be on.
So now I can go there, and where's the, I just put, push the Ladybug. There she is.
Where's the
You the best.
Jesus.
Extra credit.
Right on. Okay, hot dog. Here we go. So, if we look at this idea of solid to liquid to gas, this is called melting. Freezing is the opposite. So, melting is in this direction, freezing is in that direction. This is condensation is the reverse, or vaporization. I think I need to do this. There we go. Thank you.
Masterpiece.
There we go. All right. We also can go directly in that direction. We can skip the liquid phase altogether. Does anybody know what that change is called? Sublimation. You have the notes, don't you? And the opposite is deposition. Sublimation. I used to see that. I went to school as an undergrad at NAU. And I had a quantitative chemistry class at 7:40 in the morning. And sometimes I was the first person out at 6:45 walking along. And the snow, the sun would come out. There would be snow at night. The sun would come out. It would hit the snow and it would start to steam. So it would go directly from solid to gas. I also saw deposition up at the top of the San Francisco peaks. So I believe that the energy required for melting is around 60 calories per gram. The energy required for vaporization is something like 540 calories per gram. All right, and that's because we have these modes of motion. Solids have only vibrational motion. Meaning, if you've got something like this, and this is the standard way to depict, right, a chemical compound, you got the sticks and the balls all hooked together, that these little molecules can only vibrate back and forth around a fixed point because they're locked in place. So when you heat these things up, you heat a solid up, the molecules start vibrating faster and faster until they break the crystal structure. And so that phase change requires energy. Liquids, on the other hand, have both vibrational plus what we call rotational modes of motion. Meaning they're going to be going back and forth, right? Once you get them into a liquid, just like the solids were, they still have that vibrational motion. But now they also are rotating past each other. So that second mode of motion requires an absorption of energy. Yes? I'll just give it to you at the end of class. The last one is gas, which has vibrational plus rotational plus translational motion. So 3 modes of motion. So they vibrate, they rotate, and they translate. They have complete freedom of movement. If I took a container of water, or actually a container of ice, and I took that container of ice and I froze it solid with a thermometer, frozen into the container of ice, and here it is, solid ice. And I put my ice on a hot plate, and I started to heat it up. And I wanted to keep track of the temperature, so here would be time. We could also call that heat added, and this would be temperature in degrees Celsius. So as time goes by, we know that water freezes at 0, and it boils at about 100 degrees. So we're talking about temperature in degrees Celsius here. What temperature do you think the ice would start? If I had it frozen, thermometer frozen in a beaker with the thermometer sticking in it, everybody thinks ice is at 0, but actually ice gets much colder than 0. It gets way colder. So it would start somewhere down here at some temperature below 0. The movement of the particles would only be vibrational. As we added heat energy to those particles, they would be vibrating very slowly, and they would start vibrating faster and faster and faster, and the temperature would increase until it got to 0 degrees. What would you see visually at that point right there? You'd start to see melting occur, right? You start to see the ice start to melt. And if you monitored the temperature over the time, it might go up and down, but it wouldn't move significantly away from 0. Keep in mind, I have not adjusted the hot plate. I've kept the hot plate the same temperature. I cranked it all the way up. Where is that extra energy going that I'm adding into the solution if it is not going to raise the temperature? It's not evaporating yet. It's still ice.
Condensating.
Not to that point yet. We only have a mixture of ice and liquid in the beaker. When would the temperature... No, it's not condensing yet. When would the temperature begin to rise? What would you visually see? What would have to happen in that beaker before the temperature could go up?
It would have to be a liquid.
Ice would have to be all gone. All right? So here's where it would start melting. Here's where it would be finished melting. That's the phase change. The phase change requires energy, and it's stored in a different way. In this class, in physics, they divide energy up into a lot of different types of energy. Here we talk about kinetic energy and potential energy, the 2 big categories of energy. Kinetic energy is the energy of movement. Potential energy is energy that is stored. Now, potential energy can be stored in a lot of different ways in chemistry. We've got phase changes, we've got chemical reactions. We're going to talk about a lot of different ways that energy is stored. This is the easy kind of energy to think about because it's movement energy. Particles are moving. So if we go back to our graph and we say, all right, what was happening at this part right here, this part of the graph, was kinetic energy was increasing. The movement of the particles went faster, right? They started vibrating more. Here, they weren't moving any faster. They were moving at the same speed, but the energy added was going into changing the phase. Remember I said it took 60 calories per gram to change a gram of ice into a gram of liquid? That is the potential energy. So kinetic energy was added by the hot plate, but it didn't go into the ice as kinetic energy. It went into the ice as potential energy in that second mode of motion, right? Vibrational is the first mode of motion. Once they broke the structure of the crystal, they could vibrate and rotate, and so the energy was being absorbed by the second mode of motion during this part when the temperature didn't go up. So once it was all melted, then the temperature could rise. And it would rise and rise and rise until it got up to 100 degrees. And right before it got to 100 degrees, what would you start to see in that container? You'd see some bubbles, right? So if I was going to draw the beaker here, and here it is on the hot plate, with the hot plate up, where would you see the bubbles start to come from? The bottom. Why do the bubbles start to come from the bottom? That's the hottest spot. What's happening right there?
Gas.
It's turned into a gas, and so gas has take up much bigger space. That energy goes into moving those particles away from each other, plus that third mode of motion. Because now the particles are vibrating and rotating like crazy, right? And they're vibrating and rotating more and more and more as you add more energy. And once they can break free of the liquid, they are completely translational movement. So as a gas particle is moving around the room, it is vibrating, it is rotating, and it is translating. That third mode of motion then starts to absorb energy and water if it is uncovered. Not like a pressure cooker, that's a whole different animal. But if water is uncovered, it will never get above 100 degrees if you're at sea level, right? You can put a chemical in the water, something that you can eat that is okay. Salt. You've probably seen that on some of your directions of the food that you cook, the pasta directions or things where you're boiling water. It says if you live at high elevations, add some salt to the water. Well, what does elevation do to the boiling point? It lowers it. I lived in Flagstaff for about 5 years, and you can't get a good hot cup of coffee there because water only boils about 95 or 96 degrees. You go to the Rocky Mountains, you're looking at 93 or 92. You go up to the Continental Divide in Colorado, water's less than 90 and it boils. So it is possible. It is possible to get water. You can get it to boil above 100 degrees if you go into Death Valley. Why Death Valley? It's below sea level, and what that happens is there's so much pressure on the surface of the earth due to the air molecules smushing us, right? So here we are, standing on the surface of the earth, and next to the surface of the earth, the air molecules are really close together. As you get higher and higher up in elevation, the molecules are farther apart. So if you have an open container of liquid and you're at higher elevations, there's not as much force pushing down on the surface of the liquid as there are if you're down at lower elevations and you got all those layers of atmosphere smooshing down on the surface of the liquid. So at lower elevations, it takes more energy to make those particles change phase than it does at higher elevations because you have less atmosphere. They say the air is thinner, right? Up here. Does that mean the air molecules get skinny? There's just less of them and they're further apart. Athletes actually like to go and train at higher elevations. When I was living in Flagstaff, about I'm going to date myself here. I think it was the 84 Olympics. No, that was somewhere in there, early 80 Olympics. The West German row team came to practice at Lake Mary in Flagstaff because it was up at mile-high elevation. And if you've ever been to Lake Mary, it's long, skinny lake, and the West German guys could get on the lake and they could row back and forth, and they like to train at higher elevations. I was actually working as a grad student for a biochemistry professor at NAU, and he was able to get the coach to bring the athletes in so we could test their blood prior to them exercising and doing things at high elevation, and then throughout their stay in Flagstaff, and then at the end, right before they went down to Los Angeles for the Olympics. And it was super interesting. These guys, the shortest guy on the team was 6'10". Now, why do you suppose rowers, it was an advantage to be tall? You've got long arms and legs, and every stroke that you take with that row, right? And so these guys were enormous. We'd put them on the treadmills, and they'd be walking, and they were amazing. That was a really fun job. All right. Thank you, Larry. You're the best. You are a new tech guy. All right. Let me go back to the 2 hour. I won't hurt Gary's feelings. All right. So there we go. There's the change in physical state that we just talked about. Okay, now we're going to talk about classification of matter, which is, like I said, for biologists, is kingdom, phylum, class, order, family, genus, species. In chemistry, we do it a little bit different. We start with a classification system that has matter at the top. Anything that has mass or takes up space. I think there is a point in your notes that has this. So matter, they say, can be divided into 2 subclasses. So if we take those two, matter, And the two subclasses, what are the two subclasses that we can break it up into?
Mixtures and pure substances.
Okay, a mixture or a pure substance. All right, big difference between a mixture and a pure substance. What do you suppose the air in this room is? Is it a mixture or is it a pure substance? It's definitely a mixture. How about if you have a bottle of water? I'd say that's still a mixture. How about if you had distilled water? I'd say that's probably a pure substance. How about if you have a penny in your pocket made after 1983, I think it is. It's a mixture. What if you have one prior to 1983? Probably a pure substance. It's mostly copper. All right, so a mixture generally can be separated with physical means. So that's the big differentiation between a mixture and a pure substance. A pure substance generally needs chemical methods to separate it. One of the labs you do is we give you a mixture of salt and sand and iron filings. How could you separate those things using physical means? A magnet. Run the magnet through, get the iron filings out, right? Could you separate the sand and the salt using a physical mean?
Great.
You'd probably put some water in it. What would the water do?
Absorb the salt.
Dissolve the salt, right? You can get the salt out, right? Then you'd have the sand. How could you get the salt out of the water? Boil it. What would happen to the salt? Stay in the pan, right? And the water would boil away. Okay, those are all physical changes. If I had H2O, and I didn't have those fancy long johns in the Land's End ad, right? And I wanted to separate the H from the O, I can't do that with a physical mean, can I? I have to have a chemical method. There's a chemical method called electrolysis. It's different than the electrolysis you might have heard of where it gets rid of facial hair, right, or something like that. This is the electrolysis. You put electrical current through water, and it separates it into hydrogen and oxygen gas. And in fact, that, I think, is a good way that we could use to develop a hydrogen economy in this country. If Detroit had worked instead on developing hydrogen-powered cars, which is the cleanest burning fuel that we have that could power cars, because you took hydrogen, you put it in a car, it takes oxygen from the atmosphere, H2 and O2 make H2O, and all that drips out your tailpipe is H2O. There's no greenhouse gases, there's no unburned hydrocarbons, there's no particulates, there's no ozone, none of that stuff. It's a little drip of water out the tailpipe. The problem is in producing the hydrogen efficiently. Right now they use coal gasification, which is a very expensive process, but if we could use electrolysis to separate the H's from the O's and save the O's, oxygen gas and the hydrogen gas, we could use the hydrogen gas in our vehicles, and we would have a whole lot of advantages at that point in our sustainability. All right. If you have mixtures, you can separate mixtures into homogeneous or heterogeneous mixtures. So we can take mixtures and further subdivide into homogeneous or heterogeneous. Homogeneous is all one phase. Heterogeneous is more than one phase. So homo is one phase. Hetero is more than one. For example, my favorite example is Italian salad dressing. Right? Is that a homogeneous mixture or a heterogeneous mixture? It's hetero. There's different phases. The oil and stuff and the seasonings go on top. The water is generally at the bottom. How do you make it more homogeneous before you pour it on your salad? Yes, shake it up, right? Milk, unless it is homogenized, will separate. The cream will go to the top. When they homogenize milk, they heat it up a whole bunch, and they stir it and agitate it to break up the fat particles and suspend them. That's whole milk. If you want 2% or 1% or skim milk, you let some of the cream rise to the top, you scoop it off, and then you homogenize the rest of it. So that's what they do with milk, which is homogeneous or heterogeneous mixture. And then pure substances, finally, can be segregated into elements or compounds. So we'll take our pure substance category, element, and compounds. All right, element is only one kind of atom. A compound is more than one kind of atom chemically bonded together. So on the exam that you take on Monday, you should be able to classify any substance that I ask you to classify into one of the four categories of a homogeneous mixture, a heterogeneous mixture, an element, or a compound. And you can use this flow chart, or you can just use your general knowledge to go from one place to another. But you do need to be able to classify things into one of those four categories. So you should practice. All right, physical property and chemical property. Physical property generally is something that you can use a tool to measure: mass, volume, density, color. Those are all things that are physical properties. Generally, you use a tool, not always, but generally. Physical properties don't change a substance by measuring it. When you measure the mass of a substance, you're not going to change its chemical formula, right? You measure the density of something. You're not changing its density, you're just measuring it. A chemical property is a whole different animal. Chemical properties are things like flammability or ability for it to rust. Not all metals rust. All metals will eventually oxidize, but some are more readily oxidized than others, and we actually do a lab with that in this class. So chemical properties change the identity of the chemical when you measure it. If I wanted to burn a piece of paper, is it going to still have the same chemical formula? No. If I want to test to see if something's flammable and it burns, yep, it's flammable, it's going to be something else after I've burned it. So that's a big difference between a chemical and a physical property. Now there's chemical and physical changes as well, and that's what the lab is about this week. You're doing chemical and physical changes in lab. So you're going to put things through and you say, is it a physical change? Physical change would be things like changing phases, changing the shape, those kind of things. A chemical change is going to be something that after it's changed, the chemical formula is different, right? So it's very different. Chemical change, physical change versus properties. How do we know chemical change is taking place? Well, sometimes you form a gas. Alka-Seltzer is a good way to look at that. Or Efferdent. When I taught at Rio Salado, we did students that had lab kits, and we had to send them equipment, and they would do a lot of stuff at home. And we had to look at household substances that you could buy at the grocery store that would generate gases that you need. Well, that's not so bad. Do you know what kind of gas is generated when you use Alka-Seltzer? Carbon dioxide gas. Yep. Helps your tummy feel better, and that's why soda pop sometimes helps your tummy feel better if you have an upset tummy, because that has carbon dioxide gas in it too. Efferdent, the denture cleaning stuff, you guys are probably all too young to use that. Do you know what the gas is that Efferdent creates? Any ideas?
Bubbles up in the toilet.
Oxygen gas. Efferdent actually creates oxygen gas, and the oxygen gas helps to clean the denture. So anytime you're making a gas, that generally is evidence of a chemical change. Another one is if it lights up, or it gets hotter, or it gets colder. So if you're holding a beaker and you go, whoa, that's getting hotter, then that means a chemical change has happened, because that's not going to happen by itself, right? You have to add heat or cool something in order to change its temperature. The formation of a precipitate. Now, precipitate is different than the precipitation that you may be used to, the stuff that comes out of the sky. A precipitate in chemistry is when you add liquids together or substances together, and what happens is a solid comes out of the solution. So precipitate is always a solid that comes out of the solution in chemistry. And finally, a permanent color change. Sometimes things change color. If it's not a permanent color change, it's probably not a chemical change at all. And so there's our classification. Remember that difference between mixture and pure substances, you can separate it physically. Difference between compound and elements, you need a chemical means to change those and take them apart. All right, elements have interesting and unique names. They either come from where they were discovered, like Scandinavian, right? Or who discovered them. Let's see, what are the ones in there? I don't see any. There's an Einsteinium, but he was not the one that discovered Einsteinium. They just named it in honor of him. I always thought I think I told you guys this story already, right? If they're going to name an element after me, woodium wouldn't work, but beryllium has a nice ring to it. The letters of the elements, the first one is always capitalized, the second one is lowercase, right? So you can't do, if you want to put lead, you can't do this, right? It's got to be this. So first one is uppercase, second one is lowercase. You will need to memorize the first 35 elements with the correct spelling and their symbol. So my advice to you is to get yourself 35 3x5 cards. I'm the world's worst memorizer. When I had to take organic chemistry for 2 semesters, that was insane. You have to memorize everything. I lived and breathed with 3x5 cards. So on one side of the 3x5 card, you put the symbol. On the other side of the 3x5 card, you put the name. And then studies have shown, if you have to remember and memorize lists of useless information, right? Now this is not useless, but it is a list of information. If you have to memorize that, it's best to do it in short 5 to 10 minute chunks. So you're waiting in the bank, for the teller to come up, get your 3x5 cards out. You're waiting to drop your kid off at school, get your 3x5 cards out. You're brushing your teeth in the morning, prop them up next to the sink, work on the 3x5 cards, and you'd be surprised if you say, okay, I got 2 hours, I'm going to memorize these elements. Your brain stops after about 35 minutes of memorization, so you can't do that. Yes, question?
So you said we have to memorize the 35 symbols, and that's for the test on Monday?
There may be 1 or 2 there. I wouldn't stress and have that done for then. However, once we get to Unit 2, if you don't have those, you're going to be significantly handicapped when we start going through nomenclature. So take my advice, make your life easier, and start memorizing them right away. Yes?
You have to memorize atomic number and atomic weight.
No, that's a good question. I would not do that to you because that's information that is readily available on the periodic table. There used to be a biology teacher when I taught high school who did that to his students, and they all came into chemistry hating chemistry. He'd give them a blank periodic table and make them fill it out. They're like, oh, this is what chemistry is about? I don't want to do this, right? All right, so here's some of the ones that you have to know. Now, I got a couple of funny stories for you about how to memorize these. Some of them make sense, like carbon is C, right? Nitrogen is N, oxygen is O. But there's some that really don't make so much of a difference, right? Like antimony is SB, right? I don't know where that came from, but antimony is SB. Now, alimony sort of sounds like antimony, right? Alimony? What's alimony? When you get divorced, one spouse that makes more money than the other's got to give money to the one that makes less money, right? And it's not always the women getting alimony these days. There's plenty of men getting alimony too. Well, you could say the son of a biscuit didn't send me my alimony check. So that's how I remember alimony, right? Tungsten. Tungsten is a W, also a weird one. It looks like somebody's sticking out their tongue to me. So if you remember, tungsten looks like a W because they're going, right? Here's another good one. Iron. Ferric and ferrous are the old Latin prefixes they used to use to show the different forms of iron, which is +2 or +3. So Fe is iron. Here's how I remember it. Remember Jack and the Beanstalk? What did the giant say when he was chasing Jack? Fee-fi-fo fum. What did Jack do? I run out of there. So the sillier that your mnemonic devices are, the better you're going to remember it. Oh, here's a good one. Potassium is K. Makes no sense. A kettle is a pot. A kettle is a pot. So potassium is a K. Mercury. Here's another good one. When I was in high school, the hot guys had muscle cars, right? Camaros, Trans Am, Mercury. So I always thought, hot guys drive the Mercury, right? Another student came up with a better one. He said, what's the name of the female basketball team in Arizona?
Mercury.
Mercury. He said he remembered it because the high girls were on the Mercury basketball team, right? The tall girls, not the more commonly used vernacular for high. Copper. Copper, when you get a ticket, I had a friend who was a high patrolman. He goes, it's the funniest thing. He goes, I give people a ticket, they take the ticket, they always thank me. So I never get that. So you say, see you later, Mr. Capper. See you later. Okay, here's a good one. Now, as a woman in science, I am a feminist for sure, and I'm always espousing the abilities and rights of women to be in science. You know, they didn't used to let women go to college, and they didn't. Even the president of Harvard about 5 years ago said women shouldn't be in science because we don't have the right kind of brains for that sort of thing.
All right.
Only 5 years.
Yeah, I know.
Punch that guy in the face.
That's why I didn't go to Harvard. But here's a sexist story that helps you remember the different metals that are hard to say. Okay, so if your boyfriend gives you Tin jewelry, it turns your fingers green. Tin is a sin. Tin is a sin. It makes your fingers turn green. Silver. So it gives you a piece of silver jewelry, you go, ah, gee. If it gives you a piece of gold jewelry, you go, aw, thank you, sweetie, right? Okay, ladies, you're gonna have a good education, you're gonna make your own money, buy your own dark jewelry. Don't have to wait for any man to give it to you, right? Okay, so verse 35, and the other common ones that you've heard of before, mercury, gold, silver, those kind of things, it just will make your life a lot easier, okay? All right, enough said. So we go on to the periodic table. There's metals and non-metals. If you look on the periodic table, there's a stair-step line that starts on the left of boron. It goes all the way down. Everything to the left of that stair-step line is a metal. Everything to the left of the stair-step. To the right of the stair-step is a non-metal. So what are there more of? Are there more metals or non-metals? Tons more metals. Tons more. All of them, or most of the metals are in what state of matter? Most are in solid. The non-metals, they're solids, liquids, and gases, right? Okay. Semi-metals or metalloids are the ones that have two sides touching the stair-step. Now the metals have certain properties. Things like they're malleable and ductile. Does anybody know what those two words mean, malleable and ductile?
Malleable means you can
It can be able to be broken down.
Malleable means you can hammer it into a thin sheet. Ductile means you can draw it into wires. I have a yoga teacher who always says, at the end of our session today, I want you to be very malleable. And I want to say, so you want us in thin sheets? No, he's not going to hammer us into thin sheets. It just means that it's very flexible. Non-metals, you hit a non-metal with a hammer, it's going to shatter. You hit a metal with a hammer, it's going to bend. And that's because the nature of the atoms themselves. In metal atoms, the electrons are shared between, you have a hunk of metal, it's not a chemical bond per se, it's sort of like a whole bunch of jugglers in a room. And everybody starts with 3 balls. Like you got 3 electrons that you're juggling. And maybe you bump into somebody next to you and all of a sudden they lose 1. And now you got to do 4 for a couple of minutes and they've only got 2, right? Or maybe sometimes you got to do 5 for just a brief minute or 2. And that's how electrons are shared between metal atoms. It's very loosey-goosey. It's sort of like a community or a communal thing. Right? Everybody kind of shares the same electrons. That's why metals are very good conductors of electricity. Because since the electrons are shared and they're very loose, electricity is just simply moving electrons. You can move electrons through metals very easily. Non-metals, on the other hand, hold their electrons very tightly and they're very greedy and they don't share them at all. They don't let them go. And so that's why when you hit them, a non-metal will shatter. And it's also why non-metals do not make good conductors of electricity except for one very specific semi-metal. What's the semi-metal that actually is good at conducting electricity? Thank goodness. Not copper. Semi-metal. Remember, it's along the stair-step line with 2 sides touching the stair. Not aluminum. Aluminum is the only one that doesn't fall into that category of a semi-metal. Aluminum is not a semi-metal, even though it has 2 sides touching. It's right next to aluminum. Silicon, right? All those silicon chips in your computers and your phones and all that technology. It is a non-metal, but it is a non-metal that conducts electricity. Thank goodness for us, right? Or we wouldn't have all this wonderful technology. So semi-metals are sort of the fence sitters. Sometimes they hold their electrons loosely, sometimes they hold them a little tighter, but overall the characteristics of metals and non-metals are very, very different. So malleable, ductile are metals. Non-metals don't conduct heat or electricity. If you use a metal spoon and you're stirring a hot pot on the stove, eventually that spoon's going to get hot, right? Because heat travels just like the electricity does in a metal. Non-metals, not so much. So you can take something like plastic and wrap it over the handle as non-metal, and then it's not going to transfer that heat so readily. So there's a summary of the metals and the non-metals. All right, so atomic number. Here we go with the periodic table stuff. Atomic number on the periodic table is listed in consecutive order 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, starting with hydrogen. Now, atomic number has a lot to do with the structure of an atom. So if we look at the periodic table, I'm just going to make a shadow box outline here of the periodic table. Here's our stair-step line. Everything on this side is a metal. Everything on this side is a non-metal. And along the stair-step line are the metalloids, with the exception of aluminum. Aluminum is not a metalloid. So if we look at the atomic number, something like carbon, for example. Look at carbon. Now, every periodic table is a little bit different. The periodic table we have on the wall, it shows the atomic number up here, and then it shows the atomic mass down here. This is the atomic number. And the atomic number, does anybody know what the atomic number represents about that particular element? Number of electrons. I'm going to abbreviate electrons with a little e and a negative sign. What else does it also represent? Number of protons. And in a neutral atom, both of those have to be the same. So when you see a number like 6, that means if we're looking at the Bohr model of the atom, we haven't really discussed the different scientists and how they decide on what the model of the atom was, but the Bohr model of the atom is what we call the planetary model, where you have the thing in the middle. What do we call the thing in the middle? The nucleus. And what's spinning around on the outside of the nucleus according to Bohr model? The electrons. Okay. So electrons are on the outside, and the nucleus has what inside of it? Protons and neutrons. All right. So the number of electrons equals the number of protons in an atom. And that's why we call it an atom, because it is the base hunk of stuff that we can start with, that we combine things together. So that's where this atomic number comes from. There is something that is not on the periodic table, and it is a very confusing term. It's called the atomic mass. And it is not on the periodic table. The atomic mass has to do with, oh no, I'm sorry, this is the atomic mass. That is on the periodic table. It's the mass, see how confusing it is? The mass number that's not on the periodic table. So atomic mass is on the periodic table. Mass number is not. So we've got atomic number, atomic mass. How I remember it, the difference, when I do remember, is that the word atomic means it is on the periodic table. If it doesn't have the word atomic on it, like mass number, it's not on the periodic table. Now, these three terms are kind of confusing because they mean very different things. Atomic number, we know already, has to do with number of protons and the number of electrons in a neutral atom. So once again, if we go back to carbon, and we say the atomic number is 6, that means if I look in the nucleus of the atom, I have 1, 2, 3, 4, 5, 6 little plus charges in the nucleus. On the outside, I've got 6 electrons spinning around. So when I add those up, I have a net charge of 0. We call this a ground state atom, meaning it's got all the pieces it was born with, right? Now, I read an article once in a scholarly journal that said chemistry teachers tend to like to assign anthropomorphic characteristics to atoms and molecules. What the heck does that mean? What's an anthropomorphic characteristic? Human quality. So we say atoms want to do this. It likes to have these things. Okay, atoms don't have a brain. They don't like to do certain things. They don't want stuff. But if we use these anthropomorphic terms, sometimes it helps you remember them, right? Sometimes it helps you remember them. Okay, so even though I read the scholarly article, I continue to use anthropomorphic characteristics to describe atoms and molecules. The ground state atom means it has all the pieces it was born with. Now, born you could call the Big Bang, right? The initiation of all matter in the universe that started as a compact ball and it spewed out from the origin. So we'll call that the born moment, right? So that's a ground state atom. What can you lose? Can you lose protons or can you lose electrons? You can lose electrons. You can't generally change stuff in the nucleus. What's in the nucleus is what it was born with, right? But you can change the number of electrons. So say, for example, I took away one of those electrons in my carbon. So now I don't have an electron anymore. What's going to be the charge on that thing? It's going to be a +1 charge, and that's called an ion. And specifically, positively charged ions are called cations. Right? Not cations. I hear people call them cations, and the first time a student said that, oh, it's a +2 cation. I'm like, what's a cation? It's a cation. All right. If, on the other hand, instead of losing an electron, what if I gained one? Can you do that? Can you gain electrons? Absolutely, you can gain electrons. So now I have 6 protons in the nucleus, and I've got 7. Now my overall charge is -1 charge, and we call that an anion. So anything negatively charged is an anion, anything positively charged is a cation. Not cations and anions. Cations and anions. We got to say it appropriately here, right? Okay. And it's not a vernacular that is demographic, right? It's not like soda or soda pop or pop, right? Okay. A crazy drink, stuff that's bad for you. All right. There you go, fizzy drinks. Another one. All right, so the atomic mass versus mass number. That's an easy one to think of. Anybody know what the difference between atomic mass and mass number is? Any ideas?
I think the atomic mass is the mass of the atoms, right? And then the mass of the number is how much it weighs.
You're almost there. You're almost there. The mass number has to do you guys know, we have to introduce a new vocabulary term before we can actually really describe these ideas. Anybody ever heard of this critter before? Isotope. What does that mean? Iso, the prefix. If I had to take a language over again in college, I would have taken Latin as a science person. I took Spanish, and that certainly is helpful in the Southwest, but Latin is super helpful. What's the prefix iso? Same as, right? Isotope is something that's the same atom, but what's different about an isotope? Very good. So number of protons. So an isotope has a different number of protons. For example, every element has more than one isotope. Some only have 2, some have as much as 5. Carbon has 3 isotopes. Carbon 12, carbon 13, and carbon 14 are the isotopes. So this is their isotopic symbol. You can write them this way. I've also seen them listed like this, with the 12 underneath and the 6. So you can abbreviate, and you should know that these are abbreviated either one of these conventions, because in this class, many of you are going to go out and be nurses, professionals, doctors, scientists, engineers. You're going to be taking all kinds of standardized tests. And depending on how the author of the exam abbreviates or represents an isotope, you need to make sure that you know both of those conventions. Carbon 12 can be listed like this. This number here is the mass number. Okay. On the periodic table, this is the atomic mass. So that's not the same. This is the mass number. What does the mass number represent? So we got 3 isotopes, carbon 12, carbon 13, carbon 14. What that means is, of all the carbon in the universe, there's 3 types. Carbon 12, carbon 13, and carbon 14. They exist in a very stable percentage over time that we can predict. That's why they use carbon 12 for carbon 12 dating, because we know exactly how much there is in the universe and on the planet at any given time. What does that number represent about the isotope of carbon we're describing with that carbon 12, carbon 13, carbon 14 designation? Yes?
Is it the sum of the protons and neutrons in the nucleus?
Excellent, excellent. You guys don't need me. All right, so that must be it. Mass number is equal to the sum of the protons plus the neutrons, or in other words, the junk in the nucleus, right? Electrons are on the outside, so the mass number has to do with how many pieces of stuff are in the nucleus of that atom. All right, so if we know that carbon always has how many electrons? 6. Always 6 electrons. Carbon 12, if that 12 is the number of things that are in the nucleus, and we know that it's got to have at least how many electrons? If it's got 6 protons, it has to have 6 electrons. So if I got a total of 12 pieces of stuff in there, and 6 of them are protons, how many neutrons are there? 6. Carbon 13. Once again, we've got 6 electrons, 6 protons. How many neutrons are in carbon 13? 7. And in carbon 14, how many neutrons are there? 8. Does everybody see how we did the math on that? Okay, you don't need a calculator for that one. Right? I like to tease you millennials. You guys always pull your calculators out for everything. So that gives us information that's not necessarily on the periodic table, but it does relate to the idea of atomic mass. Does anybody know how mass number relates to this number on the periodic table, which is atomic mass. Yes?
My biology teacher kind of touched on it. So you take all the carbon 12, carbon 13, carbon 14, you add them together, and then you divide them, you get your average.
And that's a good biology teacher explanation. We don't let biologists play with chemistry very much. That's okay. We let them play once in a while. If that were true, and it was just the average, and that's how I've heard most biology teachers.
Average.
What's the average of 12, 13, and 14? 13. Is that 13? No. So somebody's doing some funny math. Must be those biologists.
Which is that you add them together and then you divide it by the number that
Still.
you have. So like
It's
you
called
have
the-
3 of them, then you divide it by 3, you get the decimal point. Like I said, she briefly touched on it.
Okay. Well, that's why we don't let biologists play. All right. It's the weighted, what we call the relative abundance. Okay. In this class, the relative abundance of males to females is usually about 50-50. When I teach 151 and 152, which is the 4 majors course, the relative abundance of women goes down to about 30%. Sorry, fellas, as you get higher in those science classes, there's fewer and fewer girls. My son noticed that. He's a physics and math major. He's like, Mom, I'm having a hard time meeting girls. I go, change your major. Right? But no, it's the weighted average. And it turns out that in the universe, the majority of the carbon is which kind is the majority in the universe? This is the majority. It's something like 95% of all the carbon in the universe is carbon 12. Something like 3% is carbon 13 and 2% is carbon 14. So it's the weighted average. And it's a super easy math thing to do, and you will have to do it. So you say, oh, well, 13 times, what's the decimal equivalent of 95%? 0.95 equals, somebody get their calculator, do that, 13 times 0.95, 12 times 0.03, and 11 times 0.02. All right, what's 13 times point?
0.35.
Thank you. What is 12 times 0.03?
0.36.
And what's 11 times 0.02?
0.24.
All right, I total them up.
Wait,
What's
11?
Yeah, that's 11 up there, right?
Whoops.
So what's the sum total of all that?
0.22 is for 11.
Well, we're going to say it's about what number?
12.01.
Approximately 12.01. Okay, I made up a few of the numbers and I rounded up things a little bit differently there. But that's how that number exists. You have to take into account what's called the relative abundance, right? The relative abundance, a statistical thing to do, and that's how it's calculated. All right. Now we are throwing a lot of math at you right at the outset, aren't we? All righty. Chemical formulas. All right. Something like, what's this stuff? Niacin. Good vitamin. When you have something like that, the little subscripts, what do the subscripts mean? How many of that thing is in a molecule? So how many carbons is in that thing? How many hydrogens? Nitrogen, there's 2. Okay, all right. Let's give you something a little more complex, since you guys are ahead of the game clearly on this one. Let's give you something like lead nitrate.
Yeah.
Classic, right? All right, how many leads are there? One lead. Now we got to do a little bit of algebra here. How many nitrogens are there? 2. And how many oxygens are there? 6. All right. What this actually means in terms of a molecular structure is you got one lead atom, and these things are called polyatomic ions. We'll learn a little bit about them in the next unit. And those are groups of atoms that stick together and carry a charge. And each of those, that means this is hooked up to 2 of those things, right? That's kind of the basic bare bones version of what that actually means. You got one lead and 2 of those units, so you have to multiply everything inside the parentheses by subscript, which is basically the same kind of stuff that you guys do in algebra. And that's it. Hot diggity dog. Any questions? Larry, thank you so much. You cannot be absent.
Never absent.
Okay? All right. Yes.
There's always
The lab?
Class.
Question about the lab. I forgot this at home. Can I like screenshot it, the lab we did with the substitute.
Do you have lab today?
Yes.
Then you need to, what time is your lab?
At 1.
Okay, well, let's do it 1.
Okay, all right.
Okay, maybe somebody can take a picture of it at home for you. Don't go home. I don't want you driving like crazy.
There's nobody there.
Okay, well, you can use your 24-hour late. You get one free late.
Okay.
So make sure that you take a picture of it and get it to me before 24 hours is over.
Okay, all right, thank you.
Thank you, hon.
The lab book is still on back order.
Really? Okay, I did post it. Didn't I post this week's lab?
I wasn't sure. I didn't get a chance to look at it, so I was wondering if it would be okay if I like look at somebody else's and write down my.
You gotta have your own. The library has ways to print things.
Okay.
And I did post it.
You've got your new in 15 minutes?
I think so. I think so. Maybe find somebody that has one and just take it to the photocopy machine.
I just had a quick question.
Yes.
For the calculators, I have this one from high school. Is that one a good one to use? I don't think it is.
Yep, you can use that one.
Perfect. Thank you so much.
Be careful though. Sometimes those calculators, you think that the sig figs are the calculators that they tell you the sig figs are appropriate, and they're wrong.
They're wrong? Okay.
So make sure you know the rules.
Right.
The calculator doesn't know the rules as I give them.
Right, of course.
We have lab today, we're turning in at the,
Yeah.
Yep, it's a necessary change. We just got married in January. I don't have any kids, so we don't have a lot of
Let's be on
Yes, ma'am.
Thank you.
and but
Just to clarify, $50,000 a year to be a doctor without
You don't have that. You left out. You have no left space.
Making sure. You told me you hate it, and you don't care about it, so I was just making a clarification. Also, what time are you, I looked at the syllabus and your office hours
I
were
wouldn't even use that much.
Yesterday, most of them, the huge chunk.